GPU Showdown Single Cards Multi-GPU. The eternal question of GPU configuration for local LLM inference continues to spark debate, with a fresh comparison pitting 4 RTX 4000 Pro Blackwell cards against a single RTX Pro 6000. The math seems seductive at first glance. 4 24GB cards offer the same 96GB VRAM as one RTX Pro 6000, cost roughly 30% less, and according to one VRAM calculator, could deliver approximately 138 tokens per second versus 93 TUF-secs for the single card on Llama 3.170B Q4. But the community quickly poured cold water on this seemingly obvious choice. The primary culprit undermining multi-GPU setups remains interconnect bandwidth. Without NVLink, which these consumer-grade cards lack, communication between GPUs crawls over PCIe lanes, creating bottlenecks that dramatically reduce effective performance. One commenter noted that finding a motherboard with 4 PCIe 5.0x16 slots is essentially impossible in consumer hardware, meaning realistic configurations would be limited to PCIe 4.0x8 at best, offering 120 GB bandwidth at best. The effective VRAM also takes a hit due to overhead. Testing suggests that 5 8GB cards deliver roughly the same usable memory as 4, with neither approaching their theoretical combined total. The consensus crystallized around a simple principle: get the best single GPU you can afford, and only jump to multi-GPU configurations when you can access proper high-bandwidth interconnects like those found in HGX A100 systems, a leap from $8,000 to roughly $70,000. For those who insist on the multi-GPU path, there's some hope in recent Llama.cpp developments. A newly merged graph split mode promises significantly faster performance than traditional layer or row modes for distributing model computation across multiple GPUs. The WRX90 platform does offer 6 PCIe 5.16 slots, though it requires expensive Threadripper Pro processors. Some enthusiasts also pointed to NVIDIA's DGX Spark as a potentially better value proposition for those with the budget for an RTX 6000, a self-contained system optimized for local inference workloads. The practical wisdom remains unchanged. Complexity in multi-GPU setups brings diminishing returns unless you're operating at enterprise scale with proper infrastructure. Auto-tuning Llama.cpp for peak performance. Configuring Llama.cpp for optimal performance has traditionally required arcane knowledge of GPU memory hierarchies, tensor placement, and the dark arts of context window sizing. A new Windows UI tool aims to automate this painful process, using what its creator calls ping-pong saturation detection and iterative binary search to find the sweet spot for any given hardware configuration. The approach systematically probes system limits, doubling context size until out-of-memory errors occur, then halving back to find the maximum stable configuration. The tuning assistant handles the complexity of multi-GPU setups by automatically adjusting tensor split values and detecting when load is bouncing between GPUs in an unstable pattern. Core optimizations like flash attention, disabled memory mapping, and 8-bit KV cache quantization are applied by default based on the developer's experience that these consistently improve performance. The tool also supports draft model configurations for speculative decoding and can handle vision models requiring separate projection files. One particularly honest admission: the current approach is overly aggressive, squeezing every drop of VRAM and leaving users vulnerable to OOM errors during extended sessions with growing context. A planned fix will reserve 10 to 20% overhead. Some previously effective optimizations have become less reliable with recent Llama.cpp changes. The developer notes that overriding tensor placement to put embeddings or normalization weights on faster GPUs no longer provides consistent speedups, sometimes actually reducing throughput. This reflects the rapid evolution of the underlying inference engine and the challenge of keeping optimization strategies current. The project draws inspiration from Llama Grid Search, while focusing specifically on the unique parameters and multi-GPU complexities of Llama.cpp deployments. Blackwell MV-FP4, Pain and Payoff. Getting native FP4 inference working on consumer Blackwell hardware required 4 days of debugging and custom C++ patches, but the results speak for themselves. 135 tokens per second on Qwen 330B MoE, using just 24.1 gits of VRAM on an RTX 5090. The secret sauce combines the efficiency of mixture of experts architecture, where only about 2.4 billion parameters activate per token despite the model's 30B total size, with Blackwell's native FP4 tensor cores. TensorRT LLM 1.20 RC4 shipped with critical bugs that prevented loading FP4 weights properly, requiring manual patches to fix the allocator using TUC VRAM and type checking incorrectly, rejecting packed INT8 weights. The guide includes practical workarounds for memory-constrained systems, including a swap trick that allows 64 GB RAM plus 64 GB swap to handle quantization, and build flags to prevent compiler ohm during model compilation. The quality argument for NVFP4 over GGUF's Q4 integer quantization centers on dynamic range preservation. NVF4 native float preserves dynamic range much better than GGUF Q4 integer approximation, even with a matrix. For MOE models like Qwen 330BA3B, this is critical. The router gating network is super sensitive to precision loss. Bad quantization leads to wrong expert selection, which the developer colorfully describes as brain damage. A proper perplexity comparison between NVFP4 and Q4KM on identical datasets would settle this debate definitively, but such benchmarks remain conspicuously absent. Predictably, the comments section erupted with platform comparisons. Dual 3090s running FP8 via VLLM achieve similar 130T per secs, while a single 5090 with Llama Q4 reportedly hits 200 times, raising questions about whether the complexity of NVFP4 justifies itself purely on speed. Apple Silicon users weren't shy either. An M2 Max achieving 62 seconds on the same model prompted extended debate about price-to-performance ratios. The broader takeaway is that Blackwell software support remains amazingly bad despite the hardware's potential, requiring significant effort to unlock native capabilities that should work out of the box. Modular RAG and open voice agents. Building retrieval-augmented generation systems typically involves wrestling with tangled dependencies and framework lock-in, but a new modular implementation promises true component swappability without boilerplate. The architecture allows single-line changes to swap LLM providers, Llama, OpenAI, Claude, Gemini, while keeping chunking strategies, vector databases, and agent workflows completely independent. Key features include hierarchical indexing for balancing precision with context, conversation memory persistence, human-in-the-loop query clarification, and self-correcting agent behavior with automatic error recovery. By default, the system runs entirely on local models, though the modular design means cloud providers can be substituted trivially. Meanwhile, the quest for an open-source alternative to OpenAI's real-time API has produced a working voice agent stack, achieving sub-400 milliseconds latency using entirely open-weight components. The architecture chains Whisper v3 for speech-to-text, Gemma 3.1b as the language model, and Kokoro for text-to-speech, orchestrated through the PipeCat framework. While not a unified, real-time model like OpenAI's offering, which processes speech end-to-end in a single model, the component-based approach offers flexibility to swap any piece as requirements evolve. One practitioner raised the thorny question of voice quality with Kokoro, noting they're training a custom 35 mem parameter TTS model to achieve more human-sounding output with emotion layers, a very tricky challenge in the current landscape. Claude's self-organizing agents. Claude Code users witnessed something unexpected. The AI spontaneously launched 3 Explore agents during a coding session, autonomously dispatching lightweight haiku-based workers to scan through thousands of lines of code before reporting back to the main orchestrator. The behavior appears more frequently when using Opus, Claude's most capable model tier, and represents a form of emergent task decomposition, where the AI recognizes that understanding a large code base requires parallel investigation. One user reported having Claude spin up 4 different agents to scour through a year of Git history for a single change, a 20-minute search that would have been far more tedious manually. The Explore agents leverage Haiku for efficiency, keeping token costs low despite the high parallelism. For users wanting more capable exploration, it's possible to override the built-in Explore agent with a custom version using Sonnet by asking Claude Code to write a same-name user agent and specify as Sonnet to overwrite it. The built-in agents support plan mode investigation with syntax like plan, investigate X issue for targeted exploration. Community members develop tools like CC Status Line to monitor context usage and token consumption in real time, providing visibility into how much of the context window these multi-agent explorations consume. The broader implication is that agentic decomposition is becoming a native capability of frontier models rather than requiring explicit orchestration frameworks. Claude simply decides when a task warrants spawning helpers. Synthetic data and security research tools. NVIDIA's open-source release of NeMo Data Designer brings industrial-grade synthetic data generation to the masses, addressing the chronic problem of datasets that look statistically reasonable but fail to capture real-world correlation structures. Unlike naive, generate 10K rows prompting, the system combines statistical samplers with LLM generation to maintain controlled distributions. Dependency-aware generation ensures that related fields, sales, revenue, commission hierarchies, actually make sense together rather than producing the data equivalent of a crypto pump and dump chart. Built-in validation through Python, SQL, and custom validators, plus LLM as a judge evaluation, provides quality assurance before burning hundreds of GPU hours on bad training data. The tool works well with local inference via VLLM, though the super chatty DeepSeek v3.2 may require switching to more efficient models for large-scale generation. On the security research front, Raptor emerges as an autonomous offensive and defensive research framework built on Claude code, demonstrating how coding assistants can be adapted for specialized purposes through what the creators describe as Winamp skin flexibility. The framework agentically orchestrates vulnerability research, exploitation, and patching processes. Its immediate practical value was demonstrated when one researcher used Claude code to generate patches for bugs disclosed by Project Zero to FFmpeg, a process requiring iteration and human review, but ultimately producing submittable patches. The tool represents an early release held together by vibe coding and duct tape, with the team welcoming community contributions for web exploitation modules, Yara signature generation, or ports to competing coding assistants like Copilot or Codex. A separate disclosure revealed a sobering SCADA vulnerability discovered during a collegiate penetration testing competition. SCADA LTS, an open-source industrial control system, exposed completely unauthenticated endpoints for importing and exporting entire system configurations, including password hashes. Exploitation required nothing more than downloading the config, modifying the admin password hash, and uploading the malicious version. A round-trip attack granting immediate administrative access to systems that control real-world physical processes like factory machinery and chemical plant operations. The vulnerability sat undisclosed for 3 years after patching due to its trivial weaponization potential and severe physical safety implications. AI solves 60-year-old math problem. In a striking demonstration of AI-assisted mathematics, Harmonic's AI system, Aristotle, autonomously proved a version of Erdos problem number 124, a combinatorics puzzle concerning the representation of integers as sums of distinct powers that had remained open since the 1960s. The problem, formally stated, given integer bases where the sum of 1 off d minus 1 is at least 1, can all sufficiently large integers be written as sums where each term comes from powers of these bases with coefficients in 0, 1? Aristotle found the proof in 6 hours. Lean verified it in 1 minute. The proof turns out to be surprisingly elementary, the kind of solution that might emerge from a math competition where short, clever arguments are expected. The mathematical community's reaction mixed genuine appreciation with puzzlement. Thomas Bloom, who maintains the Erdos Problems database, noted that, if something like this worked, then surely the combined talents of Burr, Erdos, Graham, and Lee would have spotted it. Back in 1996, when they proved the cake was 2 case. The resolution may lie in subtle definitional ambiguities about whether DTake equals 1 term should be included and whether additional GCD conditions are necessary. Importantly, the harder version of the problem, with the GCD condition that the original authors were likely targeting, remains unsolved, and Aristotle reportedly could not crack it when given that formulation. Terence Tao contributed extensive commentary and experimented with AI research tools on the problem. Gemini Deep Research failed to surface significant new literature, while ChatGPT Deep Research somewhat circularly cited the Erdos Problems webpage itself as the main source. Gemini DeepThink, when given a hint to try Brown's criterion, correctly analyzed why that approach would fail, a type of error a human expert could plausibly also make. The episode illustrates both AI's potential for finding overlooked elementary proofs and its current limitations on problems requiring deeper mathematical machinery. Abliteration gets a principled upgrade. The technique of abliteration, surgically removing refusal behaviors from language models by intervening on activation space directions, has received a significant theoretical upgrade with norm-preserving biprojected abliteration. Previous approaches subtracted normalized refusal directions from layer weights, but this is mathematically unprincipled because it conflates directional intervention with magnitude effects, disturbing the weight geometry in unpredictable ways. The new method decomposes each weight matrix row into magnitude and direction, applies the ablation only to the directional component, then renormalizes and recombines with original magnitudes, preserving the activation scale structure that normalization layers expect. The results challenge conventional wisdom that abliteration necessarily degrades model capabilities. Applied to Gemma 312b instruct across layers 1141, the norm-preserving approach achieved the highest scores on both UGI, uncensoring, and NADINT reasoning benchmarks compared to prior abliteration variants and the baseline model itself. Remarkably, NADINT scores improved from 18.72 to 21.33, suggesting that removing directionally encoded safety constraints may unlock latent reasoning capabilities suppressed by safety mechanisms. This aligns with recent observations of a safety tax phenomenon, where safety alignment demonstrably degrades reasoning performance. The technical implementation requires 32-bit floating-point precision for intermediate calculations despite 16-bit model weights and magnitude sparsification at 0.995 strength during measurement to distinguish refusal directions from outlier activations. The multi-layer intervention strategy draws theoretical support from the Hydra effect, documented by McGrath et al., which showed that ablating individual layers triggers adaptive compensation that restores approximately 70% of the original computation. Single-layer interventions fail because the model roots around localized damage, simultaneously modifying attention output projections and MLP down projections across multiple layers cuts multiple heads of the Hydra to prevent this self-repair mechanism from restoring refusal behavior. Section Bridging AI and Brain. A new architecture called Dragon Hatchling attempts to bridge the gap between transformer-based language models and biological brain models, addressing what the authors identify as the main barrier for machine learning on the path to universal reasoning models: the ability to generalize reasoning over time. The architecture is simultaneously a practical, performant attention-based sequence learning system and a biologically plausible brain model featuring neurons organized as excitatory and inhibitory circuits, integrate and fire thresholding, and working memory, relying entirely on synaptic plasticity with Hebbian learning using spiking neurons. The key contribution is formalizing a chain of reductions showing macro to micro correspondence between general attention mechanisms in language models and attention mechanisms observed in the brain. These converge as closed-form local graph dynamics at neurons and synapses, what the authors call the equations of reasoning. Unlike generic Turing machine simulations that would require billions of chain-of-thought tokens to represent a single step of brain reasoning, BDH admits a GPU-friendly formulation despite being fundamentally a graph model. The architecture exhibits transformer-like scaling laws, matching GPT-2 performance on language and translation tasks at the same parameter counts, 10 memon to 1B, with identical training data. Interpretability emerges as an inherent architectural feature rather than a post-hoc analysis. Activation vectors are sparse and positive, demonstrating monosemanticity. Individual neurons respond to specific concepts, even at scales below 100 million parameters, where such clean representations are notoriously difficult to achieve. The authors empirically confirm that specific individual synapses strengthen connections when processing language inputs related to specific concepts, suggesting a mechanism human neurons could use to achieve speech. Beyond academic interest, the work has safety implications. Scale-free systems with uniform thermodynamic limit behavior could enable probably approximately correct pack-like bounds for reasoning generalization over time, addressing the fundamental challenge of predicting autonomous AI behavior on tasks longer than validation sets. Transformers v5 and new architectures. Hugging Face's Transformers library hits version 5 with a philosophical shift towards simplicity and interoperability, sunsetting Flax and TensorFlow support to focus exclusively on PyTorch. The library now sees over 3 million daily pip installations and hosts more than 750,000 model checkpoints, having grown from 40 architectures at v4 to its current extensive catalog, while adding 1 to 3 new models weekly for 5 years straight. The modular design push of the past year has dramatically reduced lines of code for contributions, with automated tooling that uses machine learning to identify which existing architecture a new model resembles, potentially opening draft PRs for model integration. Major refactoring includes a centralized attention interface, abstracting away FA123, Flex Attention, and SDPA implementations, plus streamlined tokenization that deprecates the fast, slow tokenizer distinction in favor of the tokenizer's backend. Quantization becomes a first-class citizen with changes to weight loading, reflecting reality where state-of-the-art models increasingly ship in 8-bit or 4-bit formats. Examples include GPT-OS, Kimi K2, and DeepSeek R1. New serving infrastructure deploys OpenAI-compatible API endpoints with continuous batching and paged attention, though the goal is interoperability with specialized engines like VLLM and SGLang rather than competition. The v5 release represents an invitation for community feedback through migration guides and discussions. Meanwhile, Moonshot AI released Kimi Linear, a hybrid linear attention architecture built around Kimi Delta Attention, KDA, a refined gated delta net that outperforms traditional full attention across short, long, and RL scaling regimes. The 48B total 3B activated parameter model achieves remarkable efficiency, up to 75% reduction in KV cache requirements and 6x faster decoding throughput for context as long as 1 million tokens. On Ruler at 128K context, it shows Pareto optimal performance with 3.98x speedup compared to full attention at similar quality. The architecture uses a 3:1 KDA to global MLA ratio, balancing linear attention's efficiency with strategic full attention to maintain quality. Black Forest Labs, Flux.2 Dev also received community attention via GGF quantization releases, enabling the image generation model to run through ComfyUI's GGF loader for local deployment. Developer tools and learning resources. Arden Labs released Kronk, a Go library for hardware-accelerated local inference that integrates Llama.cpp directly into applications through their Yzma module. The project provides a high-level API designed to feel similar to using an OpenAI-compatible interface, abstracting the complexity of native Llama.cpp integration while maintaining Go's performance characteristics. This joins Arden Labs' broader training materials on leveraging Python and Go together for AI applications, plus their established service-oriented architecture toolkit for Kubernetes deployments. For those entering the systems programming world, an open technical book for the Zig programming language offers an accessible introduction to the language that's been gaining traction in AI infrastructure circles for its explicit memory management and C interoperability. The same author has produced similar introductory materials for R and PySpark, suggesting an audience of data engineers transitioning toward lower-level systems work. On the hardware privacy front, a DIY glass hole detector uses an ESP32 to scan for Meta smart glasses by matching Bluetooth MAC address prefixes against known organizationally unique identifiers. When detected, a mini LED sign lights up with glass hole, a callback to the social friction that plagued Google Glass adoption. The simple Arduino code could easily be extended to other vendors' devices or integrated into existing projects, while more aggressive future versions might attempt to disrupt Glass's operation through spoofed packets, similar to attacks demonstrated against iPhone proximity pairing. Finally, ArcAI announced Trinity Mini, a US-trained mixture of experts model with open weights and online RL for continuous learning, available free on OpenRouter for a limited time and representing their third frontier release in 6 months.